Hi guys, what's up? I am Dinesh. Welcome you all to the online lecture. In this lecture, we are going to discuss one more important concepts of the chapter vector analysis, which is nothing but your gradient of a scalar function. Here we will see how to find the gradient of a scalar function and its geometrical interpretation along with its application with examples. Okay, so let's start. If you have a scalar function v x y z, if you change x by dx, y by dy and z by dz, this is nothing but the infinitesimally small amount of change in x, y, z, then there must be the change in the function v, which you can write as dv equals to del v upon del x into dx plus del v upon del y into dy plus del v upon del z into dz. So this you can write of the form x cap del v upon del x plus y cap del v upon del y plus z cap del v upon del z dot dx x cap plus dy y cap plus dz z cap. If you take the dot product of these two parts, you will obviously get this much. Okay, so this is your nothing but gradient of a function, that is grad of v, and this is the infinitesimally small displacement vector dl. So you can write the function dv as grad v dot dl. So this is very important and you have to remember this part also. So you can write here the grad v or gradient of a scalar function v is nothing but your x cap del v upon del x plus y cap del v upon del y plus z cap del v upon del z. So this is very important part, from which you can extract the grad operator, which is nothing but your, just remove v from here, del upon del x plus y cap del upon del y plus z cap del upon del z. So this is your gradient operator or grad operator, you can say, and this will give you the physical interpretation of the gradient of a scalar function. So from which you can define dv equals to grad v dot dl. You can write this as modulus of grad v modulus of dl cos theta. So from which you can say if you fixed this vector, the magnitude of infinitesimally small displacement dl, then you can search around the direction by changing the value of theta. You will get this dv is maximum when theta equals to 0, when theta equals to 0, because cos 0 equals to 1. So you can get the maximum change in the function v is happening when there is happening when the direction the change in the function is along the direction of gradient of v. Obviously here you can see that this gradient of a scalar function is a vector quantity. Okay, you will start with a scalar and you will when you take the gradient of the scalar function, you will get a vector quantity. Okay, so this is important. This from which you will get, so dv equals to maximum when the change in the function is along the direction of change in the function along the direction of grad v. So you can see here, whenever your gradient of a function is changing, the maximum change in the function occurs when in the direction of gradient of the function. Okay, so from which you can see that this magnitude of grad V represents the slope of the tangent plane. You can say slope of the tangent plane. Okay, so this is the important concept, that's modulus of gradient of a V represents the slope of the tangent plane. And next we will see the application. Before going to see the application, let's apply the gradient of a function to some example. Okay, so let's take example and try to find the gradient of a function. Let's take an arbitrary example. V is a function of x, y, z of the form x cube plus y cube plus z cube, and you have to find grad of V. So how can you find the gradient of that function? You just apply the formula which we have already discussed. That's nothing but the gradient of a V equals to x cap del V upon del x plus y cap del V upon del y plus z cap del V upon del z. If you apply this graph, you can find here del V upon del x is nothing but your 3x square, del V upon del y is nothing but 3y square, and the partial derivative of the V of function V with respect to z equals to 3z square. Just substitute the value of del V upon del x, del V upon del y, del V upon del z. Here you will get 3x square x cap plus 3y square y cap plus 3z square z cap. This is very simple to find the gradient of a scalar functions. Let's take another example to better understand. V is equals to say x square y cube z. So this is a scalar function given and you have to find the gradient of this scalar function. So how can you find that? You just apply the same formula, that is your gradient of V is nothing but x cap del V upon del x plus y cap del V upon del y plus z cap del V upon del z. So here just put del upon del x, put the value of V, there is nothing but x square y cube z plus y cap del upon del y x square y cube z plus z cap del upon del z x square y cube z. So from which you can see the partial derivative of the function V with respect to x is nothing but your 2x, y and z are constant for this, y cube z, here x cap, plus from here you will get 3x square y square z y cap, and from here you will get how much? X square y cube z cap. So this is the gradient of the function V, x square y cube z. So I hope you understand the gradient of a scalar function when the function is of the variable x, y, z, and I hope through example you better understand the concept. In the very next video we are going to see the gradient of a scalar function when it's a function of r theta phi, that you can say in spherical coordinate system, and when it's a function of r phi z, that you can say when in cylindrical coordinate system, along with its application. Okay, so thank you for watching the video. If this video is helpful for you, then please share the video with your friends and like the video, and never forget to subscribe the channel. Okay, thank you so much.